All right. Hello, everyone. Congratulations on successfully navigating the time change in order to be here. Before we get started, I just want to remind everyone to please hold your questions until the end. If you have a clarification question that just cannot wait, you can put that into the chat and then one of the organizers will read it to the speaker. So today's speaker is Dr. Rachael Roettenbacher from Yale University. Rachael got her PhD from the University of Michigan working with John Monnier. She then spent a couple years as a postdoctoral fellow at Stockholm University and is currently a Yale Center for Astronomy and Astrophysics Prize postdoctoral fellow at Yale. Dr. Roettenbacher is an expert in near-IR interferometry, and she is going to talk to us today about her work imaging spotted massive stars. Rachael, the floor is yours.
Hi, everyone. Thank you for coming. Thank you for the introduction, Camber. Today, I'm going to tell you a little bit about the work that I do studying stellar activity, in particular with imaging. And hopefully I will be able to convince you that this is really cool work and that it does have a really important impact on studying exoplanetary systems. So to get started, I'm going to tell you a little bit about stellar magnetism. Stellar magnetism is, we know that the sun is magnetic because in 1938, Hale and Nicholson decided to put a slit from a spectrograph across a big sunspot group. And you can see on the left here that sunspot with the slit over it. And then on the right, you can see a little bit of splitting happening at the same sort of at the same region where the spot is located. And that splitting is Zeeman splitting, and we know that Zeeman splitting from atomic physics is caused by magnetic fields. So this gives us our strong suggestion that these features are magnetic. And so you may be wondering, how does the sun generate a magnetic field? Well, this is actually still an open point of discussion, but one idea is that the region between the convective envelope and the radiative core is actually a layer of shear called the tachocline. And in that region, small magnetic fields start to form, and then they build up over time, and they accumulate into a large-scale magnetic field structure. And here is just a sort of cartoon of that. The top panel shows a sort of dipolar field. And you can think about these magnetic field lines in the tachocline sort of getting boosted into the convective zone, or into the convective envelope. And over time, these field lines are sort of stuck into the convective zone, and they get dragged around the surface of the sun because of differential rotation. And that just means that the solar material at the equator rotates more rapidly than the material at the pole. And so for the sun, it's like a 26-day rotation period at the equator, and then closer to 35 days or something like that at the pole. So it's an easily observed quantity for the sun. And so as the magnetic field gets dragged around due to this different rotation rate, the magnetic field is going to start bunching up. It's going to become pretty dense in regions, and where the magnetic buoyancy is so high because of the density of the magnetic field, it's going to start popping out of the surface of the sun. And in those regions, you can see in the lower right-hand panel, you get these loops of magnetic field sticking out. And in these regions where you have the magnetic field sticking up out of the sun, you're not able to have the efficient energy transport of convection in those areas. So convection is simply just the hot material rising, getting pushed to the sides, and then falling down as it cools. And so that's the most efficient energy transport in the outer layer of the sun. But if you have this magnetic field in the way, you're not able to have that efficient motion. So your material is not going to be able to radiate away the energy as efficiently, and you're going to be cooler. And so when you're cooler, you appear darker. And so those dark regions are what we know as star spots or sunspots on the sun. And so these are just one of the stellar magnetic phenomena. So here's the spots, and you can see them moving across the surface. Yep, there we go. And you can see them moving across the surface in the series of images of sunspots, and you can see that they're dark regions against the bright photosphere. Another type of event is a stellar flare. So when you have these magnetic fields sticking up out of the surface, on that schematic, you saw that there were these loops of magnetic fields above the surface. You can see those actually in this image. You can see the actual loops of the magnetic field sticking up above the surface. And what happens here is, these are not stationary things. They're dynamic and moving around and jostling, and eventually they can actually reconnect. And that's going to sort of explode photons out into space. And you can see that in this beautiful movie here of a solar flare happening. And these are related to coronal mass ejections. They can happen from the same magnetic region, but they don't necessarily have to happen together. But these are actually when those magnetic loops don't just burst out photons, but throw out all kinds of charged particles as well. And so we know the impact of these. From looking at our own, looking at how they interact with our own. Oops, sorry, I got it. Okay. We know the impact of these by looking at our own magnetosphere's interaction with the solar events. And so we know that activity like the coronal mass ejections can have a major impact. And we see that in things like the aurora. And so this is just a beautiful picture from an instance where the aurora was quite active. And so this happens from the coronal mass ejection hitting our magnetosphere and jiggling it around and energizing the particles that are the ions that are in it. And so if these events are stronger, we know that we have to start worrying about our telecommunication device issues, and we know that we need to start worrying about the astronauts in the ISS. And so if you have really strong events like this on other stars, and your planet is just forming its atmosphere, we have ideas that these events can be strong enough if the magnetic field in the planet hasn't built up enough to just rip off the atmosphere. We have ideas about that, and we can get a realistic picture of what habitability can look like in these other systems. And here are just two papers that I've been a part of that show that the realistically habitability on like the TRAPPIST-1 systems and on the 3 planets that are in the habitable zone, it's not really a likely scenario because we see that there's so much activity on the star. And similarly, we looked at LHS 3844b, which I believe was Laura Kreidberg showed that it didn't have an atmosphere, and we looked at what had happened previously to the star, in part due to its the stellar activity of its host star, to show that might be what had contributed to it not having an atmosphere. And we also see that these have an impact not necessarily on the planets themselves, but on our ability to detect them. We know that stellar activity can cause some radial velocity shifts. And here's a nice little cartoon from Rachael Haywood, where she shows that all the way on the left is a spotless surface, and you can see the absorption line below it. And you can see that there's no real shift happening. It's just the absorption line is as it is. But then as soon as you introduce a spot that rotates across the surface, you sort of get these deviations from what the absorption line looks like without them. And you can see you can see it moving across the surface, and you can start to understand that that's going to cause a radial velocity shift. And so star spots are just one of the mechanisms that can cause a radial velocity shift. When we want to look for planets, like an Earth around the sun is about a 10 centimeter per second signature in radial velocity, and these spots can mimic that. It's a combination of the convective blue shift, which is just the blue shift signature that comes from the fact that there's convection on the surface, and then adding in the sunspot or the starspot going across the surface that then also adds to that. So not being able to fully account for what's happening on the surface can make us misinterpret the signature and claim something as a planet that it's not. So one example of that is a paper that just got published by Sam Cabot, who's a grad student here at Yale. He and I looked at HD 101-501. We used photometry from Greg Henry, who was here. And we were able to look at what the spots were doing on long term, as well as comparing that to some high precision radial velocity observations from the express spectrograph. And we were able to, Sam was able to decide to show that there's a lot more work that needs to be done before we're able to really disentangle the signature of star spots from planets. And so while I would love to be able to tell you about imaging studies in great detail on sun-like stars, they're not the easiest stars to image. So I'm going to focus on some giant stars. These are binary systems. They're RSCVNs. They're binaries with a giant primary star and typically a main sequence companion. They're tidally locked, so the companion is in a very close orbit with the primary star. They have rotation periods and orbital periods of about 2 to 3 weeks. So they're really quite extreme systems. Because they're giants, their convective outer layers are significantly bigger than the sun's, and that in combination with the close companion spinning it up means that the magnetic fields are going to be these really strong and create these gigantic spots. And we see these spots readily in photometric observations, as well as signatures of it in like calcium H and K variability. So these are a well-known type of spotted star where the spots are really quite extreme and really great for studying with imaging techniques because they're so big. So I'm going to tell you about 3 different imaging techniques building up. The first one is with photometry. It's a light curve inversion technique. And what we do is we just look at how the light curve changes over time because of the spot rotating in and out of view. When the spot comes into view, the light curve is going to decrease. It's going to get dimmer. And then when it rotates out of view, it's going to get brighter. And so here is just an example from a Kepler light curve where you have shown here. And then below it are surfaces that were reconstructed with light curve inversion from that light curve. You can see 3 different phases, which are all labeled underneath it, corresponding to the same light curve above it. And so the great thing about this is that we can do this with any star. If it shows a rotational modulation, we can invert it and get an idea of what the surface looks like. It's great because we can constrain what the spot longitude is, and it doesn't require too much data. Though this is Kepler data that I show here, we can also do this with ground-based observations without a problem. And it doesn't require this good of phase coverage either. So it's a really versatile technique in that regard. The problem, though, is that we don't get very good constraints on latitude. We get some information. We can get some relative spot information, particularly, this is particularly bad when we only have one band pass, which is the case with Kepler, for example. But if we have multiple band passes, we're able to see the difference in how the spot appears on as it goes across the limb and use limb darkening to actually constrain where the spot is located in latitude better. We can't get any information about the star out really from this. We have to give the algorithms all sorts of information on like the inclination of the star, the temperature of the spot, the temperature of the photosphere, that sort of thing. We have to put that information into our inversions. So we can't readily extract any information about that from the inversion. And we can only actually see things that are rotationally modulating. So if you have a spot on your pole that's facing you, that's not going to rotate in and out of view. So we're not going to be able to see that sort of signature. So it's only things that really do go in and out of view that we can reconstruct with this method. So here are 2 examples using ground-based observations of RSCVNs. The top is a single rotation, so it's just 4 views of the same star. You can see that these spots are huge, is why I like to include that one. And the bottom is for sequential observations. And the important thing to see there is that we can actually see over time that the spots are changing shape. And so I already mentioned Kepler. As you know, it's stared for 4 years. So we have these beautiful long light curves that we can actually do this with as well. And so we chomp up the Kepler light curve into single rotations and recreate the surface, and we can actually track how the spots are evolving over time. And here is an example. This is actually not an RSCVN, but I love how beautiful and clear that light curve is, so I have to include this one. We think it's actually a pre-main sequence star, but this is 5110407. And in this example, you can see that there are two spots rotating at different rates. You can see the differential rotation happening, with the higher latitude spot appears to be rotating more slowly. We're actually centered on a latitude for the lower latitude spot to be held as constant as possible. So the higher latitude spot's moving to the side because it's moving more slowly around the star. And this really highlights one of the problems with the light curve inversion. You can see in like the lower left corner that when the spots are at the same longitude, we can't actually resolve them. So that's really just highlighting some of the issues that we have with the technique. But we can still do fun things. This is a pseudo-Mercator plot where I have a whole bunch of these images of the star flattened out into a rectangle. So you can see the spots coming and going and being hard to resolve with the technique and that sort of thing. And so why would I want to do this? I want to do this because I want to track the spots over time. I want to see how they're evolving over time. And one thing that I've been doing recently that I feel absolutely obligated to include, because I've been spending like all of quarantine working on it and I couldn't not include it in here, is that I'm trying to do a differential rotation study on these spotted Kepler stars. And so the idea is that we cross-correlate the images, and we do that line by line in latitude. So we break up the surface into this grid and we just cross-correlate the images from like one rotation to the next. And you can take this a step further and you can do this cross correlation for more rotations apart and end up getting ideas of how long the spots live and that sort of thing. But I've just been focusing on the differential rotation to see if we can pull out how the spots move with respect to one another at different latitudes with just these images. And it turns out we can get some information. I'm not going to go into the details of this plot. It's more complicated than it looks like it is, but but the idea is that there's a shape here, and that indicates that the different latitudes are rotating at different rates is the gist of this. And the lines are all just a bunch of different methods to try to detect that. And so that's exciting, and I'm still working on it, and I felt absolutely obligated to include it because I've spent so much time on it recently. So look out for that soon. Another imaging technique that I use is Doppler imaging. It uses spectroscopy, and the idea is that you look at the absorption line and you see how the spot moves through it. This is the same thing that we saw earlier in the little cartoon from Raphael Haywood, with the line being sort of filled in a little bit as the spot was rotating in and out of view. Here's a nice movie of it. The fun thing about this is you can see that we start seeing information about spot latitude. The higher latitude spot, like the one going by now, affects only sort of the core of the absorption line. But whereas the lower latitude spot, and there's one on the equator coming around now, is going to affect the whole line. And so it's going to be this shift across the whole thing. And so we're able to use that information to understand where the spots are actually located on the surface. And again, we have longitude information as well. The problem with this is that it requires a lot more observation. It's a lot more observationally expensive than the photometry because we need high resolution, high signal to noise observations. We need bright stars and we need big telescopes to be able to get high resolution spectra from them and have them be bright still and have like the high photon count. And it also requires pretty good phase coverage in order to be able to see the different features and be able to reconstruct the surface. And so we also like to restrain this to stars that are rotating pretty rapidly because we want to be able to assume that the spots moving across the absorption lines are going to be pretty constant as they move across the absorption line. So we're not, everything we see, we anticipate to be part of the structure moving across and that we're not seeing evolution of the spot at the same time. So here are some examples, again, pseudo-Mercator plots, so the whole star plotted out. These ones don't show the part of the star where you can't see due to inclination, so you can see that your latitude 0 is not in the middle of the plot. So these are two RSCVN stars, two of my favorites, Sigma Gem and Zeta And. And the really important thing I want to point out about Zeta And is that there's a dark region at a latitude of positive 90 degrees, which is the pole. And that is that's the polar spot that I mentioned earlier that we can't see with light curve inversion because it's not going to rotate in and out of view. So this is an example of being able to see it here. And some work that I've taken part in over the summer was looking at differential rotation of Sigma Gem. So these are actually sequential images of the surface. This is work that's recently been submitted and is going to be sent back with revisions soon, I believe. And so these are sequential surfaces, just 4 of them. We have a whole set of 7. And you can see that there are changes over the time, and we were actually able to measure differential rotation with these as well. And so again, the fact that this plot is not just a straight horizontal line suggests that we're able to actually see different rates of rotation on the stars. So fun stuff. The next technique is interferometric imaging, which uses aperture synthesis imaging. And so if you're not familiar with interferometry, you have your light from your star way off in the distance, and it comes in and it hits one telescope before it hits another, because your interferometer is actually a set of disconnected telescopes. And so the idea is to have those disconnected telescopes act as one big telescope, where the baseline of the distance, which is the distance between the telescopes, acts as like the diameter of your telescope. So your light comes in, and you have this problem where it hits one telescope, and then a little bit later it hits another telescope. And so we have to do fun things to account for that. We have these mirrors on carts that move around to artificially lengthen the distance that the light has to travel, such that it hits the telescopes or it comes from the star at one point in time, it hits the telescopes at different points in time, and then ultimately hits your detector, your beam combiner, all at the same time. So it's a fun, complicated thing, and there are lots of mirrors involved. But that's just the very basics of how interferometry works. The cool thing about interferometry is that we're able to actually see the stars as they appear on the sky. So there are no degeneracies that we had with latitude. There's no confusion about any of this. We can see the star exactly as it is on the sky, and we can see the spots exactly as they are. And the great thing about interferometry is you just build bigger and bigger interferometers, and you can see smaller and smaller features on the surface of the star, which is great, but it's also probably its biggest limitation, because we are very limited by the length of our interferometers. And as a result, we presently require our stars to be pretty large. Stars are on the order of about 1 milliarc-second, which is quite small, but in order to be able to see features on it, we need to see sub-milliarcsecond resolution. And we also need pretty bright stars because of all the mirrors that are involved. And so the best option for seeing those features, those sub-milliarcsecond features on the star, is actually to use the CHARA array, which is Georgia State's Center for High Angular Resolution Astronomy array. It's a 6 telescope interferometer. The telescopes are 1 meter in size. They actually just got funding to build a 7th telescope, which is very exciting. And so your light comes in and it hits these individual little telescopes. It goes through some vacuum tubes, and then it goes into that L-shaped building there next to that big giant central dome. And that's where we have our movable delay lines as well as our beam combiners. So the CHARA array effectively makes a 330-meter telescope. And I used to use the Michigan Infrared Combiner, which used all 6 CHARA telescopes in H-band. And so the images that I'm going to show you are all with this combiner. It's recently been upgraded to MIRC-X, which is in collaboration between the Universities of Michigan and Exeter. And it uses all 6 telescopes. It has H and J band capabilities, and they're working on testing the polarization options of it too. So here is an example of an image spotted star using MIRC at CHARA. So this is the original MIRC instrument. These are snapshots of the RSCVN Lambda Andromeda. This is work by Rob Parks. This was part of his PhD thesis, and I believe that it has recently actually been accepted to APJ, I think, which is very exciting. He took these sort of snapshots of the star. This is a very slowly rotating star, so he just took these cool snapshots and could combine a couple of nights together when necessary to really see what the spots looked like. This is fantastic, but my ultimate goal was to actually be able to compare the different imaging techniques. So I wanted something that was going to image the entire star at once. So something more in line with the Doppler imaging and the light curve inversion. And so we developed this technique of imaging the whole star at once. And we do that by observing the star throughout its rotation and overlapping the interferometric observation. So the idea is that each point on the surface of the star is going to be mapped to by multiple nights, hopefully making something that's more robust and definitely making something that's more analogous to the Doppler imaging technique. And so the great thing about doing interferometry is you are very often surprised with fun things that I have found. And so these stars are giant, they have a giant star and a much fainter companion. And we actually were able to find, to detect the companion, which was known because of the spectroscopic radial velocity shift, but it hadn't been detected prior to this. So we found that we were able to detect it. The dark ring around sigma gem A is the actual spatial extent of the primary star on the sky. And then the other little ellipses are actually just the detection of the companion. So those aren't the size of the companion or anything. That's just where we detected it. We actually can't resolve the companion. We combined that with some beautiful radial velocity data because we initially didn't have the secondary, but we told our collaborators, hey, we found it. So maybe you could find it too. And sure enough, they were able to pull out the signature of the secondary. So we combined this beautiful radial velocity curve with our beautiful detections and got a really nice orbit. And the cool thing about this is that we're able to really constrain and understand the system, which hopefully would improve our imaging. And we believe it did. And so in our imaging, we had 3 simultaneous data sets of photometry, spectroscopy, and interferometry. And so we imaged them individually with their own techniques. And so using light curve inversion, we were able to see this surface. This is Sigma Gem in 2011, and we could see these 2 strong spot signatures. And this could be the result of or these spots could actually be at the same latitude, or they could be at different latitudes, and it's just a limitation of the light curve inversion technique. And so we looked in Doppler imaging, and we looked at the simultaneous interferometry, and we saw that these 2 spots actually aren't at the same latitude according to the other imaging technique. So this is really highlighting one of the limitations of light curve inversion. And we also see that there's possibly this higher latitude stuff happening that we don't see in the light curve inversion, but we see it in the Doppler imaging. And we don't really see it in the interferometry, but to be perfectly honest, we don't have good phase coverage around 90 degrees longitude. So it's possible that our one night of observation wasn't sufficient to be able to detect this. So qualitatively, this is great. We were able to see and compare these images, but we wanted to go a step further, and we actually had those surfaces and created the light curves, or reconstructed the light curves of those. So here in the same order, the photometry on the bottom, and then Doppler imaging and the interferometric on the top, we're able to compare the observed light curve in gray to the reconstructed surfaces light curve in the red dashed line. And fortunately, the light curve inversion line matches the data pretty well, which is great since that was the input for it. The Doppler imaging, which was independent of the photometry in the middle, shows the same shape, but a different amplitude. And then the interferometry is similar, shows the same shape, but a different amplitude. And these differences are potentially due to the fact that the imaging techniques are sort of looking at different things. Like in the interferometry, we're in H band, and then we have to convert it to V band. That may have caused some problems. We don't think it did, but it may have. And the Doppler imaging is sort of a fundamentally different thing, where you're looking at a few absorption lines and trying to reconstruct the entire surface and its features from that, as opposed to one sort of overall value, like a broadband filter. So this was encouraging in that we got the same shape. So there seems to be consistency among the different imaging techniques. But because we didn't have very good phase coverage in the interferometry, we went after this again in 2012. And we were able to, again, look at these images and see the differences between them. And so the fun thing about 2012 is that it was now a much more spotted surface. It was a lot more complicated. And you can see that there's these bright and dark regions around the equator, limited, at least in the light curve inversion, by the fact that that you can only resolve so much with the technique. And so then we also see these higher latitude regions, which we probably didn't really see very well, at least in the interferometry in the 2011 data. We now see consistency between those. So I like to think of So I think that the interferometry is really emphasizing the good things about both the other techniques. We did the same thing where we took the surfaces and recreated the light curves, and here are those. The interferometry and the light curve inversion show similar shapes in their light curves, but again, the interferometry, the amplitude is a bit off, and the Doppler imaging is not terribly consistent with it. And so here are what the star looked like on the sky in 2011 and 2012 in H-band from the interferometry. And what I would like you to take away from this comparison is that we now have a better idea of what the strengths and weaknesses are, so we can better understand what the surfaces are that we're looking at with the different techniques. And of course, I'm biased in thinking that the interferometry is the greatest thing, and we should be able to do this to all of our stars, but you know, maybe we'll get there someday. So what's next from here? I'm working on a series of projects now to do more imaging, and unfortunately I don't have any new fun images yet. I was hoping to, but you know, the pandemic. So hopefully I'll get some of those and be able to show them soon. But the one project that I'm working on that I'm really excited about is we have interferometry data of Sigma Gem from last November, and we also have simultaneous Zeeman Doppler imaging. So Zeeman Doppler imaging is like Doppler imaging, but we're looking at the polarization information in the absorption lines and using that to reconstruct the actual magnetic field of the star. So this will be the first study where we are able to combine or investigate anyway what the magnetic field looks like and compare that to the actual spots on the surface and see what kind of correlations we can find there. And so that's really exciting. It also overlapped. We also have the Zeeman Doppler imaging, or yeah, the polarimetry data. There we go. Overlapped with TESS observations, but unfortunately those happened in like January or February of this year, which is not good for CHARA because it snows a lot. So we don't have simultaneous of all of those, but we do have some ground-based photometry for Sigma Gem as well on that. So that I'm very excited about that. And I really wished I had been able to show you some fun things from that, but soon, I hope. I'm also looking at Zeta and again. This was the one with the polar spot. We have observations from 2011 and 2013 where we saw big changes in the spot structures as well as this polar spot. And the idea is to do the first study of differential rotation with interferometric observations. So the idea of cross-correlating the images that I'm doing with the photometry, I just stole that idea from Doppler imaging because that's a technique that they've been using for many years to measure differential rotation in their images. So I'm going to apply these techniques to some interferometric images to see if we can understand what the surface of how the surface of the star changes over time and compare that to Doppler imaging results for differential rotation. I'm also working on applying this to main sequence stars and in particular Epsilon Eridani. This is a light curve inversion with most observations, so space satellite. And you can see that there are small spots on the surface. And these are actually resolvable with CHARA. The star is actually quite big. It's like over 2 milliarcseconds. And so these features would be detectable with CHARA and MIRC. So I'm working on that. I have MIRC-X data for that as well. So I'm at Yale and I'm working with Deborah Fisher, and she has the express spectrograph with its high precision. And so we have ideas of trying to combine those observations with some express spectra. And in the future, we're developing a plan to use the Spica instrument, which is going to come online in 2022 at CHARA, and it's invisible wavelengths. So the advantage of it being invisible wavelengths is that we're able to get a higher resolution with it. And so we're hoping to combine observations from that and Express to look at Epsilon Eridani and other main sequence stars to get more details on the surface. And the ultimate goal with that is going to have simultaneous observations to be able to pull out what is caused by the star spots in particular. And so one of the results from the paper I worked on with Sam Cabot that I mentioned earlier was that he found that having a series of observations in high cadence for spectroscopy is going to be what's necessary to be able to really understand what the stellar activity is at that time and to be able to remove it. So we're aiming to have high cadence spectral observations at the same time as the images to be able to disentangle those. And this is the ideas for how to really take apart the pieces of the radial velocity. The radial velocity observations is a really hot topic now. And so there are lots of different techniques that are being tried to work on that. And so just very briefly, I'm working on some larger scale things. I love looking at individual stars. It's so much fun because you can learn so much about each star, and they're all different in very unique ways. But I'm trying to see if there's some overarching characteristics of the spots that might be able to help us when we don't have the advantage of being able to interferometrically resolve the star at the same time as we're trying to look at the spectra and that sort of thing, because most stars we can't do that with. So I'm looking at the many thousands of active stars in the Kepler archive. There are about 43,000 that have 4-year-long light curves of active stars. So I'm trying to take this and I'm chopping it up and making all these surfaces. And here's just Kepler, which I'm working on this now of getting all these images and soon tests. And so the idea will be to understand what kind of stars have what kind of spots. Is there any way that we can see that, there's always spots on this type of star of, particular spectral type and age? Are there typically larger spots or typically smaller spots? Anything that we can extract from this to try to help understand these things better. And so I'm going to also work on this to build a catalog of spot affected spectra to try to understand what the impact is, and if that might be a useful thing to help disentangle it. And also there's going to be all kinds of sort of extra fun things about stellar activity that are going to come out of this, and more studies of differential rotation, active longitudes, which are a really fun thing where the spots tend to form and disappear at the same longitude over and over and over again. And so that's something that we don't really understand why that happens, but we see it. And also understanding the flares. And I mentioned flares earlier, and I showed you the pretty video. And that's something that a lot of people are actually working on now, is understanding the flares and how they're correlated to the spots on the surface, if they are, if they aren't, and understanding how that really affects the habitability of the system. And so finally, I just want to tie it all together. My ultimate goal with understanding as much as possible about star spots and stellar activity in general is to really understand how stars evolve with activity and how different masses of stars have different behaviors with the activity. And so the idea is that ultimately this sort of thing might be useful for updating stellar evolution theories to account for activity better, to understand stellar dynamos better, perhaps even providing a good boundary condition for these models. And predicting whether a signature that we see in radial velocity is actually from a planet or from a star, or from a star spot, and really understanding what the habitability of these planets really is once we do a better job of characterizing them. So with that, I'd like to thank you for your time, and I'm happy to answer any questions.
All right, thank you so much. I think it's just amazing that we can actually resolve these star spots and watch them as they move across the star.
Why?
So if you would like to ask a question live, you can raise your hand in the participants tab. If you would rather have me or one of the organizers read the question, you can type it into the chat. And I see we have a question from Everett.
Well, thank you for an excellent talk. I really liked the comparison of the three techniques. I was wondering, for the light curve inversions, like what kind of assumptions go in? Because I think you can get these are not unique solutions, and I was wondering what assumptions go into those.
Yeah, so they are definitely a very degenerate thing. There's a whole family of solutions that can recreate the same light curve. Some of the assumptions that we put in are that the spots are dark on a bright surface. That eliminates a whole bunch of solutions. We put in the assumption of the inclination, which sometimes we have measured, sometimes we have to guess. And when we guess, we put in a range of them. We have to give constraints on the spot temperature, on the photospheric temperature, on the limb darkening coefficients. Yeah, there's a lot of assumptions that go into it. We try to make them as realistic as possible, though, so it's the most realistic, but also we understand that it's probably the simplest solution that can create that surface.
Okay, thank you.
So I actually have a question also about the comparison between the different techniques. So when you were showing, I think it was the flux as a function of time and how well the different techniques were able to reproduce the shape of the profile. And then for, at least for Sigma Gem, the Doppler technique underpredicted the amplitude and the interferometric technique overpredicted the amplitude. So I was just wondering, is that like something that has to do with those techniques where you would expect them to always under and overpredict respectively, or does it really depend on the structure of the particular source you're looking at?
So ideally, we would have the appropriate light curve to compare for each technique. So the interferometry was observed in H band, and we should have had H band photometry, but I screwed up the observations. So we don't have H band photometry to compare to that. That was why I shouldn't have been allowed to plan observations by myself as a graduate student. So if we had had that direct comparison, I think I would be able to say more definitively what's causing that and how we're to interpret it. But because we had to convert from H band to V band, I don't know that I can. And this is literally our only example of it. So I think we need to study that a little bit more. However, with the Doppler imaging, we do see, not just in these images, we do see that there are other instances where the amplitude of the reproduced light curve is smaller than the observed light curve. And so it is a thing that happens in other things. And we think that that's because they're fundamentally different. Because as I mentioned, that we only use a few of the absorption lines in the Doppler imaging. The ones that my collaborator is Heidi Korhonen on that, and she uses 4 different absorption lines to make the images and combines, and they work all together to make the image. And 4 absorption lines isn't going to, completely tell you what's going on the entire surface, because they're all temperature sensitive things. So there could be some information that we're missing with that, but it's also sort of untenable to use all of the absorption lines. So we try to use the ones that are most affected by the spots in order to recreate it. So I think that might be part of what's causing that difference in amplitude.
All right, thank you. Question from Joan.
Oh, hi, thank you so much for a really interesting and wonderful talk. My question was about, maybe you covered this, but like people have questions about whether if you have a hot Jupiter close to a young star, that there could be some magnetic interaction between the 2 components. And I know one of the systems you studied was a binary system. Do you see any evidence for that kind of magnetic interaction where you might have some spot patterns on the 2 components that are related? Is that something that can be studied? And can we get any insights into star-planet interactions from those kinds of observations?
Yeah, that's a great question. There are efforts to find the connection between the spots and the planets, as well as stars that are close together. And one way to look for that is to look for active longitude spots. So those star spots that keep appearing in the same region, because that's going to suggest that the magnetic field is pretty static at that longitude. And if that happens to be facing the companion, that can really give us some insight into whether they're connected or not. And so that, I know people are actively looking for that sort of thing. And we have seen active longitudes on some stars. So it is suggestive that this is a phenomena that happens, and just really pinning it down and being able to draw robust conclusions from that. I think it's something that still needs to go on, but I think there are enough people now excited about stellar activity on planet hosting stars that I think we're going to see a lot about this soon.
Thanks.
All right, question from Gilda. If you want to unmute.
Yes, can you hear me now?
Yes.
Okay. My question is about stellar activity versus age, and whether the interpretation of should be dark spots versus bright regions. I see that Greg Henry is listening to the talk, but his point is that sometimes you see photometric activity wherein older stars can be more related to bright regions associated with higher magnetic activity. Are most of your stars young?
No, actually mine are the binary systems, the RSCVNs are actually quite old. They're evolved into giants. So the assumption is made that they're dark spots on a bright star because we want to assume that the same mechanisms that we see on the sun are happening on those, but in a more extreme way. Doppler images have actually shown bright spots on them in some places. Sometimes they happen at sort of at similar longitudes as the dark spots, so they could just be a problem with the reconstruction. Sometimes they do appear on their own, so it does seem that there are bright regions as well. But I don't know that, I can't definitively say if, I mean, I can't definitively say one way or the other, but I do know that there have been bright spots found on some of these stars with Doppler imaging in particular. The light curve inversion, you kind of have to assume that, you know, it's one way or the other, which is, you know, one of the limitations of the technique, really. And with the interferometry, everything we've seen so far just appears to be the dark spot on the bright photosphere. But again, this is just one class of stars that we've done this with. So maybe when we expand to the main sequence stars, we'll be able to see something different and exciting and new.
Right, because you mentioned Epsilon Aries young, but its main sequence. So we have a couple of systems that are farther. One is similar to Epsilon Aries, we think, is HD 189733, which has a hot Jupiter. It's at 16 parsecs. So maybe that's one you can try to push your measurements towards. It's a very well-studied system in terms of the planet.
Interesting. I know, I think like Eridani and 61 Sig are like the only ones we can do imaging on right now with MIRC, but maybe when Spica comes, what was the number of that again? HD
189733, and there have been magnetic field measurements.
Yeah, that would be a great candidate then.
Yes. Okay, thank you.
We have a question from Neil Turner in the chat who writes, thanks for the great talk. Could you say more about the prospects for using one or more of these methods to correct stellar radial velocities for the spots in order to improve our sensitivity to low mass planets?
So the ideal, I think, would be able to have the radial velocity observations and have the interferometric observations at the same time, and to be able to really see what the spots are on the surface exactly with no question, and be able to identify what the signature of those spots is and be able to remove that from the radial velocity. That would be the ideal. Realistically, we can do a lot with simultaneous photometry. We can get an idea of what the spots are on the surface, and we can get an idea of sort of, we can do a decent job, I think, of pulling out that signature from the radial velocity signature, but understanding that we might not be getting it all because of the degeneracies of the problem. Typically, the stars that we are from my understanding of radial velocity studies, the stars that we're looking at tend to be more solar-like. So their V sin I value is going to be pretty low. So the ability to reconstruct the surface with Doppler imaging from those observations is going to be pretty limited. So I don't want to say that we could point to that and be like, is this a realistic surface? Can we see what, what's realistic of this? And, is part of it possibly a planet? I don't know that we can do that because of how slowly they're rotating, but I think there is potential from the other imaging techniques to work in combination with the spectra. And that's something that like here at Yale, we're working on, and there's a whole big group trying to study how to disentangle this. I know you had Lily Zhao speaking in September, and she's leading, I don't know if she mentioned it in her talk, but she's leading this whole study to have where the group provides express data as well as light curves from Greg to researchers trying to disentangle the signatures of the radial velocities. And I think there's like a dozen groups working on this problem to see how to take them apart and see what the signatures are. And so this is something that people are actively working on, and hopefully I'll be able to have a better answer soon of an example of being able to really take them apart.
All right, next question is from Serena.
Yeah, I did not have a raised hand button because I'm the host. So when I think it really, I might have missed it when you answered to John. See, the bright spot is not kind of expected if you actually, even if when we look at the chromospheric images of the surface of the sun, some spots are brighter than the other side. And especially if in the binary, if the magnetically they are coupled, and then some areas would brighten up, while the spots are probably related to that, but the near to the spots, that is not expected to have actually bright spots. And I was expecting that actually you might actually see those bright spots related to the position of the spot if you have more data points.
I think you would need different wavelengths than what we typically look in, because we typically look in with the photometry, it's B and V, and in those wavelengths, like the sun you're not going to be able to see those bright spots. You need to go into the higher or the shorter wavelength regime.
UV, basically.
I'm sorry?
You need a UV observations for that, I guess.
Yeah, exactly. And we don't really have those observations for these stars. I mean, we've never tried to get like Hubble to look at the star at the same time, which we probably
you don't need a Hubble. Probably you can see maybe in the B band shorter wavelengths. Photometry.
Well, in the stars that I've looked at, we haven't seen a big deviation in the shape of the light curve between the B and the V, for example. And so I don't know. So the stars that I've looked at, I don't think have had these bright spots because the shape has been the same. So it might be different on different stars because, again, the stars that I look at, are a very particular type of star. So perhaps if I deviated much further away from the RSCVNs, we would be able to see something. But that is a very good point.
I believe you can. I mean, Greg is on, right? He can tell us because his photometry is in the optical. I think there is. Hello, Greg. Hello.
Yes. This confusion between bright spots and dark spots is not as bad as it sounds. Very simply, young stars are spot dominated. They have much more dark spot area than they do bright facular area. A main sequence star like the sun is facularly dominated. And as the magnetic cycle increases, the brightness increases. The opposite is true of the RS-CAN bands or young solar stars. When the activity increases, the stars get darker because they're spot dominated. And that change, that switch from spot to facularly dominated occurs pretty far on down toward solar age main sequence stars, which is about the limit of ground-based photometry. I can resolve long-term variability in sun-like stars to a millimag or maybe half a millimag at best. And that's roughly where the sun is. And that's where my sensitivity to spots trails off. So the stars that you're working with to this point certainly are spot dominated, and your assumptions of dark spots and your image inversions are good assumptions, I think.
All right, thank you for that. Do we have any final questions for Rachel? If not, I encourage everyone to unmute and thank her for a really cool talk.